let's take a look at some triangle theorems. I guess the first triangle theorem we always learn is the angle sum of a triangle is 180 degrees. Did you ever do the one when you were first told this where you actually cut the edges off the triangle, line them up, and oh look, they form a line. Yeah. So that's I guess an informal proof of 180 degrees. Let's do a more formal one. Sorry, before I do the formal one, there of course, if I wanted to use, as I was mentioning before, I would write this plus this plus this is 180, because that is what the theorem says. Alright, let's do a proof. In order to do this one, I'm going to construct a new line. DE parallel to BC, and it's going to go through A. From there, which I guess in a way is the same as cutting the angles off and placing them on a straight line, but instead of cutting them, I'm going to use alternate angles. So DAB would be the same as ABC, EAC would be the same as ACB. We know those three add up to 180 because they form the straight angle DAE. So if I substitute back in, I get that the three angles of the triangle add up to 180. The often forgot theorem about triangles, and that is the exterior angle of any triangle is equal to the sum of the two opposite interior angles. A lot of people waste time by forgetting this because they end up doing an angle sum of a triangle and then go, oh look at angles on a straight line. But and that's why we have this theorem, to save doing that. So angle ACD would be the same as adding angle A and angle B together. That's exterior angle of a triangle. The way I name the triangle is I name the vertex where I'm referring to the exterior angle first. So that's just, I mean, you don't have to, but I think that's a nice way of doing it so it directs people to see, and that's where I'm talking about the exterior angle. So CAB. Let's prove that one. So I'll construct another parallel line. This time it's going to be parallel to BA, and I've got some corresponding angles that would be equal, and again alternate angles, and so therefore, well, ACD, there's two different ways I could describe ACD, and if I substitute into the sum on the right hand side, I get the result that I'm looking for. So let's expand it out to polygons, and we know the angle sum of a polygon is 360 degrees. So yes, all four. Notice we don't draw a little picture of a rectangle or something like that. Triangle is an acceptable symbol to use, but once we get past that, we just name the polygon. So ABCD is 360. Proof? Well, if I construct in our diagonal AC, what I've basically done is split the shape up into two triangles. And we just said the angle sum of triangle ABC is 180. ADC would also be 180, so if I add them together, I must end up with the interior angle sum of ABCD. So we get 360. If it was a pentagon, well, the angle sum of any pentagon is 540. Same idea. I'll just pick a vertex, draw in the diagonals. This time I've split it up into three triangles. So, and each of those triangles have an angle sum of 180, giving us a total of 540. So we can generalize that. So any polygon, I can do that. I could pick a vertex and draw in all the diagonals. Now you're always going to have two less diagonals, because when you join that vertex up to all the other vertices, two of them will be sides of the shape itself. So you get two less than the number of sides. This one's an interesting one, exterior angle sum. So if you get all of the exterior angle sums of the shape, and it doesn't matter how many sides, it's always equal to 360. So there you go, exterior angle sum 360. So there's our triangle theorems.